approximately 1412 Q. So that's the result. Now if we divide the value by the charge, we would have the potential, and that is we would be able to divide it by Q, and we would know that the potential would be 1412, so that the capacity would be the inverse value. So we would get something like 1 millifarad of capacity. 1 millifarad is 1000 of a farad, of the unit of capacity, and we now know that the Earth, as a lonely ball in the universe, has some capacity. Now this is quite a big value for a capacitor. We have been able to create bigger capacities only very recently. So this is more or less the important point. If there are some charges on the Earth, they can easily flow into the ground, and therefore the basic course of physics mostly states that the zero potential place is the ground. Now we will try to find out the capacity of other objects during seminars. Just this was the first point. Please, are there any questions? Well, I will make a short break of 5 minutes, because more or less that's the time we have reached now. So please, 5 minutes break. After that break, I will again switch to questions as to capacity, and then we will go on. Well, hello. Are there any questions? It seems there are no questions. Thank you. Now, I would like to stress that the lectures are important to have some interaction together. I'm very sorry that we have only the possibility to do that through internet. But anyway, I will ask you for something. I will try to get your attention, and sometimes I will intentionally make mistakes on my whiteboard. Please do not hesitate and tell that. Once you see the mistake, and you will be the first one to say that there is a mistake, that might be chat or microphone, you will win a small prize. Let's try to do this to see that really we have some interaction. Is that clear? Okay, so shall you see something like a wrong definition? Shall you see any other mistake? Shall you think that there is a mistake? Anyway, tell it, because if you think that there is a mistake, I have the possibility to tell you why that thing is correct. And there is interaction, which is an important part of a lecture. So, if you can, if you see that, proceed. If you report a mistake which is not a mistake, that's not a big fault, and anyway, that's not something that would make me angry. It will help me to make better lectures for you. So, fine, we have established a value that is called capacity, and this capacity is an important value. We produce as a mankind a lot of capacitors, and these capacitors are devices which can store charge and then release it again back to the circuit. For that, there is an important value that if you buy a capacitor, you are interested for, of course, in price, but as an electrical engineer, you are mostly interested in three things. The first is the capacity, the value of the capacity. So you go and buy a capacitor of 1 microfarad, for example. Then there is a second quantity which is very important, and that's the maximum voltage this capacitor withstands. So you have the capacity, the voltage, and then there might be a third value which is important in order to find out how long the capacitor would hold the charge itself, or how it would behave at high frequencies, and that's the quality factor of the capacitor. Let's stick to the first two values, and let's, for example, investigate what that means. So we have a capacitor, our big capacitor created by a zero charge or zero potential at infinity, and the earth ball has a nice property which says that the voltage you can put on that is infinite. But it's not tiny, it would not fit into your mobile phone. So for less space recommending capacitors, we always have the electrodes in a finite distance. And there is something that we have not been talking about yet, and that's the breakdown voltage of the capacitor and the breakdown field strength of a material. Now let's talk about that a little bit. If you have a kind of material, for example, free air, that material consists of many particles which are inside, and if you put there a big field strength, then any charge that is there is exposed to force. And depending on the material, the force can cause that particle bearing charge to move or not. Now let's talk it in free air. If you have free air, some gas, and there is a charged particle, it would move. For example, if I put there two electrodes, anode and cathode, one is positively charged, the other negatively, we have a field strength at this direction. Just let's consider that there is electrically neutral gas. Then there would be no movement, no force. But once we have there a single ion, it would move depending on its sign of the charge, if it is positive or negative, it would move to negative or positive electrode. And it will be running faster and faster because there is a force, and if its speed it gains before it collides with another particle in the air gets big enough, it will create a new ion in that collision, and therefore we would get an increasing number of ions just caused by the electric force. And if this is the true, we would get a discharge. So even if the material is non-conductive, shall there be one single charged particle and the electric force is strong enough, we may get a number of charged particles and therefore conducting media and therefore the discharge. Now the question is, where does the first charged particle come from? And the reply could be, well, that is, for example, due to X-ray radiation. It might be the radiation of radioactive substances under you. It might be even the cosmic radiation, but if there is sufficient time, we will get some charged particles in any gas. And therefore, if there is sufficient force, we would get ionization and the discharge. Now the question is, a valid question is, well, as engineers we would like to have some estimation. So what is, for example, the maximum field strength for air? Well, it depends on the content of water. So if you have a lot of water in the air, high humidity, you would get lower value of the maximum field strength. But anyway, the breakdown value for normal air is 3 megavolts per meter. So two plain electrodes at a distance of 1 meter could have the voltage up to 3 megavolts, and the air would withstand that. But if you get over this voltage, there will be a discharge. And it is important to note that if the air is polluted or if the air was very humid, the value would decrease. So this is an important point, and this is why, for example, we cannot have our high voltage lines very close one to the other. We have to bear in mind that when the voltage line crosses mountains, there could be fogs, and we have to to put the line into the safe operation condition by making all the voltages or the conductors under high voltage distant from the other ones. So this is about breakdown. Now if we have a material which has high breakdown voltage, then we can create a capacitor with solid dielectrics, for example, but anyway, any material has the capacity for the, or any material affects the capacity of the capacitor because it has some permittivity. And also it affects the maximum voltage of the capacitor because there is some breakdown electric field strength. Now, the thicker you make the dielectrics in a capacitor, the higher you have the breakdown voltage of the capacitor. But as the electrodes are more distant, you decrease the capacity. So you have some trade-offs when creating a capacitor. Now, I would like to go on to a connected topic, which is the energy in a capacitor. So let us, for example, consider a capacitor which has got two planar electrodes and those electrodes are quite big when compared to the distance between those two electrodes, so that we have achieved a field inside which is homogeneous. For such a capacitor, there is a textbook equation for the capacity which says that the capacity of this capacitor is proportional to the area, the surface of the electrodes, and inversely proportional to the distance of them. And then there is the important property of the media, the dielectrics, which is called permittivity, and depending on its value, we obtain the capacity. So this is the simplest equation to get for a homogeneous field and a capacitor. Now, at the same point, the energy contained in a capacitor, provided that the media is linear, is given by W is equivalent to 1/2 of C V squared. Now, why that is the true? Well, just imagine that you charge the capacitor from zero. So at the beginning there is no energy, no field, no charge, and you insert some charge. And it's a linear capacitor, so that we have voltage here and we have the charge Q. And if you insert some charge, that is, you push some current into the capacitor, you get some voltage. The slope of this curve is given by the capacity of the capacitor. The bigger the capacity is, then the slope would be less steep. And now, by pushing the current into the capacitor, you get some product. Voltage by current multiplied by current, that's some power. So the power depends on the voltage and current. Current is given by the transport of charge against time. So in fact you have the area under this curve as the energy in the capacitor, and as you can see, This is one of the formulations. 1/2 comes from the area of a triangle. You can also formulate it in a different manner. For example, the voltage can be expressed using charge. So, for example, you can get it like 1/2 of Q over C and that's it. Now I would like to attract your attention to another question. So let's say we have a capacitor and we have some energy stored in it. Or we have two charged balls which attract each other so that they can produce force, and there is some work that can be extracted out of this system just by allowing those two balls to approach each other. Now the question is where the energy sits. Does it sit only on those two balls? Does it sit inside the balls? Is it somewhere around? And this is a tricky question, but a kind of philosophy. But anyway, what if we try to find out what would be the value of the energy around those two balls, around those charges in the space where the field exists? As you know, at the beginning we have said, okay, we have some strange thing that allows objects or charges to interact with each other on distance, at a distance. It's not a stick, not a rope that you can pull. It affects on a distance. That's the field. So the field that is able to affect other objects like charges at a distance is present around those objects, the area where we can find the effect of that charge we have pragmatically defined as the area where the field exists. So if there is a field, it should have some energy. But how to find an energy in an empty space? How to define or find the energy density? And that's what we will do now. I have written a big W as the energy. The energy, of course, is measured in joule in our system of units. But what if we try to define the energy density? So we say, okay, we have two charges. There is some total energy of the field. But we would like to investigate how this energy is distributed in the field around those charges. And to do that, we would have to find out some quantity that could be measured and that could sit in the free space around that. And this is the energy density, which we call small w. So the small w is defined like the amount of energy, which is big W, divided by a small volume. So let's find a small volume delta V, and we would have there some energy delta W, and this is the ratio. Important, this V is not voltage, this is an element of a volume. We have not enough letters in our alphabet so far. So, This is the energy density. But how to find the energy density in a free space? We have some field there. So let us do this simple trick in our minds. Let us have a very small capacitor that would measure the field. And we will compose the capacitor in a very clever way so that we will put its electrodes so that they are collinear with the equipotentials of the electric field. Or I can tell there are perpendicular to field strength and field density. So we have put a very small measurement capacitor, which in fact has a very thin electrodes, and we have put that into the field, and we have positioned it so that it does not affect the field at all. Because if you put a very thin conductor to a place where there is already an equipotential, you will not change it, because the surface of a conductor is an equipotential anyway. So there was an equipotential, there is an equipotential now, the field is not changed. And the capacitor is so small that we can consider both electrodes as planes. So we have this small capacitor that is constructed using two planes and the separating dielectrics. But in order to be able to handle curved fields, we need to have the capacitor very, very small. Well, okay, we will have a differential capacitor where the dimensions would be dx, dy, and dz. Let's put in here. So this is the dx, this is the dy, and there is dz. So the capacitor has two electrodes with the dimensions dx by dy, and they are spaced or separated by a layer of dielectrics, which is infinitesimally thin with the dimension dz. To distinguish z from 2, I would just cross it here. So we have a small capacitor. The volume of that capacitor is differential. The volume is, delta volume is dx by dy by dz. So it's a very small capacitor, and we know the volume. We just multiply the dimensions dx, dy, dz. Now, let's find out the capacity of this capacitor. Well, okay? Or let's find out the voltage between those two electrodes. So the voltage from here to here, as we have reached differential dimensions, the field strength is homogeneous inside the capacitor, which means that we can calculate the voltage as a simple multiple of field strength and distance. The field strength is E, the distance is dz. So the voltage between those two electrodes is dz multiplied by field strength E. So we have the voltage, big V, is the differential in Z multiplied by field strength E. That's the voltage of the capacitor. Now, let us find the surface of the electrode. That's dx multiplied by dy. So now we have the voltage, we have the surface, we have the distance. To find out the capacity of the capacitor, we just put those dimensions into this equation. So we have dx dy, that's the surface, We have dz, that's the distance, and there is the permittivity epsilon. So the capacity of this tiny capacitor would be C would be equivalent to epsilon, and we would have dx dy in numerator and dz in denominator. So this is the tiny capacity of this tiny capacitor. Now we can establish the value of energy, the energy content in this capacitor. It is C V squared divided by 2. So we would get the energy, big W, as epsilon dx dy divided by dz, that's the capacity, divided by 2 and multiplied by dze squared. I'll do that. So we have 1/2 of permittivity multiplied by dx dy and divided by dz. And now we have to multiply that by e dz squared. So we multiply by e squared dz squared. We have here dz in denominator and dz in numerator squared, so we can cancel the terms, and we obtain that the total energy in that small capacitor would be 1/2 of epsilon dx dy dz e squared. Now this is the total amount of energy in this small capacitor. If we want to obtain the energy density, we would have to divide it by the volume of the capacitor. And we already know that the volume is dx dy dz, so that's the product of those three differential dimensions. So if we divide the total energy, happily we already have the dx dy dz term in it. So the energy density we have obtained, small w, which is the big W divided by delta volume, is 1/2 epsilon E squared. We can rewrite this term. If we multiply permittivity and field strength, we know that we obtain field density, electric flux density. And so the other formulation is 1/2 of E d, where E is the electric field strength and d is the electric flux density. So in this calculation, we have found out that we can find the density of energy in an electrostatic field if we know the flux density or electric field strength at that point. So we can get some meaningful value, which is called energy density, and this density is obtained from electric field strength or from flux density at that point using a simple equation. Now later we will find out what this is good for, but please bear in your minds that the field has some meaningful value for field density also in the energetic sense, and that there is some energy in the electromagnetic field at any point where the field exists. Questions, please.